So we saw that if we have a metric space and two sets which are closed, let's say A and B, and they're disjoint from each other, I can construct a function which is 0 here and 1 here. Okay, in a metric space, this was true in a rather strong sense, more than we can expect in a arbitrary topological sense. But we can do something close enough to that if just the space is normal. So let's take X to be a topological space. The Urison lemma, so since I've called it, so that's the theorem. It's a lemma of Urison, in fact, because it's a lemma for an even more important theorem of Urison, the metrizability theorem. But the theorem, which is the Urison lemma, says that if X is normal, and we have sets A, B in X closed and disjoint, so A intersection B is empty, then we have a function, there exists f from x to 0, 1. This is a continuous function, continuous map. Without continuity it would not mean much. So such that f restricted to A is identically 0 and f restricted to B is identically 1. So this sort of result is very nice, because when we started with only a set topological conditions, open sets, closed sets, those containing each other, and out of that we manufactured real numbers, not the class of real numbers but a function to real numbers. Okay, so which is nice, not those surprising, because the point with real numbers, or indeed the interval 0, 1, is it's determined by its order structure. So it's not that real numbers, while important, are not something that we just have to treat as a black box. We know what real numbers are, and indeed that is the idea of the proof. So let me just draw a picture first. What we'll do is we have A here. We'll construct a set U0 that contains A, and then out here we'll construct the set U1 which is going to be open, and B will be outside U1. In fact, it can be the complement of U1. So we think of it this way, and we want a function which on U0, little bit bigger than A, we are going to construct a function which is going to be 0. It's going to be 1 on U1, and what we'll do is we'll model the level sets. We'll construct the functions by constructing the level sets, that is the sets where something has a value, or rather where something has less than some value, the sub-level sets of the function. So sets where f of x is less than some value, and not for all A, for special values. We'll construct it for half, then we'll construct it for quarter, and construct for 1/3. But what do I even mean? We don't have f, we want to construct these sets. Well, we'll construct sets with the appropriate properties and then define f in terms of them. So that is the sketch of the proof. So let's first start by constructing U0 and U1. So by normality, okay, I will deliberately write there exists U0 and V open such that A is contained in U0 and B is contained in V, and U intersection V is empty. Okay. So that is, since U intersection V is empty, U is contained in X minus V. Remember that this is closed. Hence, what we know is U0 bar is contained in X minus V, which is contained in X minus B, and this is what we'll define to be U1. Okay, we could have simply taken the complement, but that's not good enough. To establish continuity, we'll need not only these sets to be nested, but to be nested in a strong sense. If one boundary meets the other, then the functions, it'll be ambiguous how we define things there, and if we make choices, we will end up failing with continuity. What we need is that if I take the closure of one of these sets, it should be in the interior of these sets. Okay, so we will construct sets First I'll say what they are and then for what values of P. So let me say UP in for, well, I have to say, well, I might as well say what they are, otherwise it's hard to frame the sentence. We construct sets UP associated to not just 0 and 1, but to dyadic rationals. We could instead do it for all rationals, but that's not needed. It's cleanest to do it for dyadic rationals. So P is going to be m by 2 to the n. Okay, and dyadic rationals such that, in fact, between 0 and 1, but such that if P is less than Q, we have a strong nesting. UP bar is less than, is contained in UQ. Oh, and UP is open. Okay, so the closure of 1 is contained in UP is open for all P. Okay, we'll really construct them. So U0 and U1 are as above, and they satisfy the key conditions. Okay, and now we can define, we define inductively on n UP for P in equals m over 2 to the n, where m is odd and 0 is less than or equal to P is less than or equal to 1. Okay, so we define them for 2 to the 0, which is 0, and 0 and 1. Well, 1 did not exactly follow these, so this is in lowest form. Okay, so I could just say in lowest terms, so that the 0 doesn't have to be an exception. So lowest terms. And we have 0 is less than or equal to, P is less than or equal to 1. So to be concrete, let's construct U half first. So we have U0 here, we have U1 here. And what we know is U0 bar. So we have U0 bar is contained in U1. Okay, so U0 bar and where was I? And the complement of U1. Are disjoint closed sets. Okay, so what does that tell you? So you have U0 bar and U1 bar. Now we use the same thing, method that we used earlier. Okay, hence by normality there exists U1 and V, let's say, we'll reuse V since we discarded the previous V, open, such that U0 bar is contained in U1 and the complement x minus U1 is contained in V. Oh, sorry, there exists U half. We want to construct V half. So U0 bar is contained in U half, x minus U1 is contained in V, and U half intersection V is empty. Therefore, U half is contained in x minus V, which is closed, which implies that U half bar is contained in x minus V. Okay, and x minus V is in turn contained in so U half bar is, which is in turn contained in U1 because U1 was a neighborhood. Also, what about the other end? The other end is that also U1 bar is contained in U half. That was the condition here. Yeah. So sorry, U0 bar is contained in U half. So U half is strongly between these two. Okay. In general, when things are in lower terms, if we have constructed UI for in general, if we have constructed ui for I equals m over 2 to the n, and n is, let's say, greater than or equal to 0, even already this works, and we construct, okay, and we define u, well, let me call it m over 2n plus 1, so m odd as follows. So m is odd, so m minus 1 is even. So m minus 1 by 2n plus 1 is m odd. Instead of writing m odd, okay, so let's write m odd, but m is going to be 2k plus 1 for some k. Okay, so we define um, it has to be 2k plus 1, so it will be between 2k by 2n plus 1, which is k over 2 to the n, as follows. By normality, there exist open sets u m over 2 to the n plus 1 and v such that uk over 2 to the n is contained in um, and now again we are going to use the complement of a close of an open set, which is going to be closed. Sorry, uk bar is contained, this is closed, we have this, and then we have the other complement of the next thing, which is uk plus 1, and so, and something is contained in v, that is going to be x minus uk plus 1 over 2 to the n. Should clarify. So these are the sets between which you have to be. So if it was u quarter, it would be u0 and u half are these two sets, and we find something outside the closure of u0 and the closure of these. Okay. So I didn't emphasize, but previous hypothesis tells you that u0 bar and the complement of u1 are disjoint. So these two are in fact disjoint closed sets inductively. So, and hence we can find these sets contained here. So it's crucial, the strong containment gives strong containment. The strong containment tells you these two closed sets are disjoint. So we find v such that this is contained, and x minus uk plus 1 by 2 to the n is contained in v. Then u m by 2 to the n plus 1 is as required. Or let me spell it out, okay, as required. That is, if I look at the previous set, that is uk by 2 to the n is contained in um over 2 to the n plus 1, but this, not just this, but this closure, and it's not that, I'm not dividing the sets, it's the index which is divided. Over 2 to the n is um over 2 to the n plus 1, and I'll clarify one more detail. U bar of m over 2 to the n plus 1 is contained in the next set, which is k plus 1 by 2 to the n. Hence, what happens is that hence p is less than q implies that up bar is less than uq for all sets defined so far inductively. So by induction, these are the two biggest sets by induction, the ones that are contained here. Everything else is contained in this or in its interior or contains this. And so for the new set, we'll continue to form the relations with the old sets and also with the new sets by transitivity of inclusion. So we have got a nice setup where we have got these nested sets, and we have u1 here, and each point is contained in some u1, except for points that are in some UI up to U1, except that some points are actually contained in B itself, in which case they would want to be 1. So in fact, we can recover the function from these sets. So define f from x to 0, 1 as f of x is the smallest number such that x, so x is a point. Look at which of the sets it's contained in. X in UP, P dyadic. Well, there's a problem. Otherwise, you could be in 1 itself. So I'll just add the point 1. So if it's in none of the sets, it gets the value 1. Otherwise, if it's in some UP, then it gets the value P is dyadic. And the lemma is that f is continuous. Okay, so for that it's worth looking at the picture. Let's ignore the extreme case, which is at 0 or 1, which is a matter of just checking a couple of details. What about the main case? I have some point here. Okay, and there is the value, by the way, this infimum is just any real number, because even though it's an infimum of dyadic integers, that gives the dyadic integers completed give you the real numbers. So we have this point x, and we are looking at a p. So that p is in this set. So if the value is here, okay, and we want to show continuity at x. So proof, we'll show continuity at every point. Okay, so fix x in x. Okay, and now let's assume x is dot belong to a and b. If it belongs to a and b, you'll have to deal with these cases. So these cases is exercise. Let's look at the main case. So what happens to this value? So let epsilon greater than 0 be given. Okay, so by definition of f of x, there exists p dyadic. First of all, there exists p dyadic integer such that x belongs to UP and p is less than f of x plus epsilon. Let's throw in a by 2. I think it's not really needed, but it costs us nothing. Okay, so what about on the other side? So we have found a point. So x is in UP, and then if I take any integers, also pick q, since these are dyadic integers are dense, dyadic, such that q is in f of x minus epsilon by 2, f of x. Okay, then x does not belong to UQ. Okay. I might have to do a little more work. Let's give ourselves a little more room. Yeah. So I want to look at a closure. Okay. Fine, let's do this in a slightly less efficient way. So Q is here. Okay, and so let's call that Q prime. Let's call it Q prime, and Q in f of x minus epsilon by 2, Q prime. So it's strictly less, also dyadic. Okay, the reason I bothered to do this is because on the Q side we have to take a closed set and we want an open set. So we'll give ourselves abundant room. So here is Q prime. X is not here already, and then Q is even further down, but it is still close to f of x. Okay, so then what happens is, so what do we know from this definition? Then we know that Qx does not belong to UQ prime, and hence x does not belong to UQ closure. That's why we gave some room. Okay, so you let W be UP minus UQ closure. So UQ closure is actually contained in UP. Okay, then X belongs to W, and by definition if Y or whatever belongs to W, f of Y is in f of x minus epsilon, f of x plus epsilon. First, the upper bound is by definition this Y is contained in UP, and it's not contained in UQ bar, and so it's not contained in UQ, which means that the f of Y is actually greater than UQ. So it's not contained in UQ bar, it's certainly not contained in UQ, so UQ is not in this set. So the infimum can be at most Q, it can't be strictly less than Q, or we get a contradiction, and so we see that f of Y is here. So we managed to construct a continuous function from purely set theoretic hypothesis to the very concrete object, which is real numbers. As I mentioned earlier, we are really using the linear ordering structure of real numbers rather than an algebraic structure. This is part of the reason we introduced order topologies.